Hello, in this video I will show you how to run a log linear model, also how to interpret the result from a log linear model. I have found on the internet there are some videos that tell the viewers how to run log linear model, but did not quite get into how to interpret the result of a log linear model. And that is what motivated me to produce this video. So I am going to show you not only how to run a log linear model in some statistical packages such as SPSS, but also how to interpret the result of a log linear model. So we're going to use SPSS to do this, and we also do the same thing with other statistical packages such as SAS or R. Well, now on the screen, as you can see, that we are in SPSS, and here is a data set. Let's call it Boy Scout data set. We have three variables: Boy Scout, delinquent, and income. Let's see what they are. First variable, Boy Scout, we have two levels. Level 1 is labeled as 1 and is yes, the boys are Boy Scout members, and level 2 is no, the boys are not Boy Scout member. Variable delinquent also have two levels. Level 1 is yes, your boys become delinquent, and level 2 is no, boys are not delinquent. And variable income have three levels. So level 1 is boys are from low income family, and level 2 is boys from medium income family, and level 3 boys are from high income family. So we're going to use these three variables to run a three variable log linear model. Let's first go to weight variables using frequency. So let's weight cases by frequency. It's okay. Now let's do the model selection. Let's go to Analyze, Log Linear, Model Selection. So we place all the three variables into the window we call factors. First, let's define the levels for each variable. Boy Scout have two levels, so minimum is 1, maximum is 2. Same for delinquent, so minimum 1, maximum 2. Income has three levels, so minimum is 1, maximum is 3. Okay. Then we go to select model. Let's just run saturated model. Then we go options, residual, frequencies, residuals, parameter estimates. We just use the default backward elimination, and we're okay. So now we see the printout. First table just shows us the data information. We have three variables, how many levels for each level, and then we have this convergence information. The model converges after one iteration. Then we have this table that show observed counts and expected counts and related residual. Since we are running a saturated model, the observed count and the expected count are exactly the same. So all residuals are 0, and therefore you cannot calculate a chi-square value either. Then the next table shows us KB and higher order effects. The top part of the table shows us that if you remove the term of one level or higher, what's going to happen to the expected count. For example, 1k equal to 1, that means that if you remove the first order term second order term and the third order term, what's going to happen to the expected counts. As you can see, that the p-values is very small. That means that if you remove all three levels of terms, the expected counts will be significantly different from the observed counts. So you cannot remove all three levels together. And k equal to 2 means that if you remove the second order and the third order terms, and that what's going to happen. As you can see, the p-value is also very small, so you cannot do that. And the k equal to 3 means that if you remove the third order term only, and p-value is going to be 0.927. That means that the expected counts are pretty much the same as the observed count, so you can remove the third order term. The bottom part of this table tells if you remove each layer, each order term by itself, what's going to happen? When k equal to 1, that means that if you only remove the first order term, what's going to happen? As you can see, that you cannot do that because the p-value is very small. And if you only remove the second order interaction effect term, and p-value is also very small. But if you only remove the third order three-term interaction effect term, therefore that will cause p-value is very large, so you can do that. Okay. And next table is parameter estimates. So we're going to come back to this table later on to try to interpret parameters from log linear model. And next is the backward elimination statistics that tells you how each of the term is removed from the model. We start from a saturated model which contains the three-way interaction terms, and that's called the generating class. And at the end, this term is removed because if you remove this term, the p-value is very large. That means that after you remove this three-way interaction effect term, the expected counts are pretty much the same as the observed counts. Do not change the model significantly. Okay, therefore we can remove this term. After this term, three-way interaction effect term is removed, we have this as generating a class. We have interaction between Boy Scout and delinquent, interaction between Boy Scout and income, and interaction between delinquent and income. At the end, the model decides to remove the Boy Scout and delinquent interaction term because that would lead to a p-values very large. So if we remove this interaction effect term, it will not change the expected counts significantly. But if you remove Boy Scout income term or delinquent interaction term, that would change the expected count significantly. So you cannot remove these two interaction terms. Okay. So after these two, after Boy Scout, after Boy Scout delinquent term is removed, we have generating class Boy Scout income and delinquent income. And then the model decides that you cannot remove either because you remove either, that would result in a very small p-value. And therefore, what's left in the model are these two generating class. So this is going to be the bound model that we are going to use. So now, we're going to use these two second order interaction effect terms, also all the main effect in our log linear model. So now, let's the last model tell us, last table tell us that if we keep these two interaction effect terms at the generating class, we're going to have this goodness fit table that result in the expected counts are pretty much the same as observed counts. So now let's go to run this log linear model. We go to analyze log linear general. So let's select these three variables into these factors window, and let's choose model. We're going to build terms. So we first going to build. Pardon me. So we're going to first select interaction terms. So remember, we're going to have one interaction term is between Boy Scout and the income. So we put it in. Also, another interaction term is between delinquent and income. We'll also put that in. In addition, let's change here main effect. So we're going to include all three variables as the main effect. So these are going to be the term in our log linear model. We have two terms of second order interaction effect, also have three main effect variables there. We continue, and let's see what we want from the printout. We need frequencies, residuals, estimates, and that's probably all we need. Let's continue, and okay. So now we have this printout. We have first table is data information, three variables, and also what labels they have. And the model converged after 20 iteration, and this is the same goodness of fit table that we saw early on that shows that based on our model, the expected counts are not significantly different from the observed counts. That is what makes these p-values very large. Now, next table gave us cell counts and residuals. As you can see, that this column gave us observed counts, and this column gave us the expected count based upon the model that we use. They're pretty much the same. That lead to residuals very small, and that is what made this model to be good. And next table is the parameter estimates. So now we are going to focus on this cell count table and the parameter table, and to show how we interpret the result of a log linear model. Let's first export these two tables. For the first table, we right-click, you choose export, and you choose that you're going to save that as an Excel spreadsheet. You choose where you're going to save this. So I do not do this since I already saved this table early on. Okay, do the same for the second table. You export that as a Excel spreadsheet. Okay. So now let me open up the two Excel spreadsheet. This is the first Excel spreadsheet which show cell counts, observed count, and expected count from the linear model we run. And the secondary Excel spreadsheet is parameter estimates. Okay. Now we're going to use these two tables to show how to interpret the result of the parameter of a log linear model. Now let's focus on the relationship between Boy Scout and income. And to do this, let's based upon this cell count table, let's build a little contingency table. We call it expected count. Okay. Expected count. So there are two we have two interaction effect term. One is between income and the Boy Scout. Another is between income and the delinquent. Let's first take a look at the relationship between Boy Scout and income. And for this reason, we build this continuity table. And here is on the row is Boy Scout. We know it take two labels, and take label 1 is yes, so boys are Boy Scout member. The label 2 is no. And for income, it's three labels. Okay, let's put it here. So income, three labels. Okay, it's low, median, and high. So that's let me show you this table I built here. I type in the table here. Okay. So here we have yes, Boy Scout membership, no, and low, and median, and high. Let's use some color to highlight this little table here. Okay. So we have three borders. Okay. Now we're going to use the numbers from the count table to fill out this expected count contingency table. Okay. Now first let's look at Boy Scouts who are from low income family, medium income family, and high income family. Okay. Now Boy Scout, here is first variable is Boy Scout, and second variable is delinquent, yes or no, and third variable is income. Okay. Then now to get the information about Boy Scout who are from low income family, we need to find out Boy Scout, yes, who are from low income family. Okay. So Boy Scout members, they come from low income family, they could become delinquent or not delinquent. Therefore, for this part of the count, we need to add up this number are the Boy Scouts who are, let me use color to highlight this value. This yellow number is the Boy Scout who are from low income family but delinquent. But also we need to add this value to this number. This number tells us the Boy Scout who are from low income family but not delinquent. So we need to add up these two values to get information the Boy Scouts who are from low income family. So now we'll only look at the relationship between Boy Scout and income, but we need to add up those Boy Scouts who become delinquent, also who not become delinquent, and that is these two values we need to add them together. So this is a cell is F4 plus F7. Okay. So for this cell, we need to add up F4 plus F7. So that's the value. And next cell, Boy Scouts that are from median income family. And here is Boy Scouts who are from low median income family. This is this green cell who become delinquent. But also there were Boy Scouts who are from median income family who are not delinquent. We also need to include that value as well. There's two green cells. So the two green cells can be calculated as F5 plus F8. And do the same for the Boy Scouts who are from high income family. This is let's say this is blue cells, two blue cells. Okay, so that is Boy Scout who are from from high income family who are delinquent, and the Boy Scout who are from high income family who are not delinquent. Okay, F6, F6 plus F9. Okay, now we are ready. We do the same for the boys for those boys who are not Boy Scout members, and that is the second part of the table. Okay, so for this, so this is Boy Scout. This value plus this value are boys who are not Boy Scout members, but who are from low-income family, and this is F10 plus F13, that value. And here, now we have this part. Boy Scout, that are the boys who are from medium-income family who become delinquent or not delinquent, but they are not a Boy Scout member. So that's F11 plus F14. F14. And finally, we try to find all the boys who are from high income family, either delinquent or not delinquent, but who are not Boy Scout members. Okay, these are two blue cells. Okay, so here is no, they are F12, F12 plus F15. So now, after fill out all these cells, let's take a look at this contingency table. Look at the contingency table. This contingency table shows us the, let's make this less decimal points. Okay. Now, this contingency table shows us this relationship between Boy Scout and Boy Scout membership and income. Okay. Now, to make the interpretation more straightforward, let's focus on a 2x2 subtable within this contingency table. Okay. Let's copy this whole table into a new place. Now let's focus on the relationship between high income and low income boys. Okay, let's focus on this a little, this 2x2 subtable. Okay, here, focus on this 2x2 subtable. Okay, within this 2x2 subtable, we're going to try to examine a relationship between Boy Scout members and non-member versus whether they come from low-income family or high-income family. To do this, let's first calculate odds. We know odds are basically the ratio between two probabilities. For example, for low-income family, the odds who are Boy Scout member versus who are not Boy Scout member can be calculated by using the ratio between 54 and 211. Okay, so that's how we calculate odds for Boy Scout membership, yes or no, for low-income family. Okay, this is how we calculate odds. Odds is between, we use 54 divided by 211. Okay. We do the same for high-income boys from high-income family. We should copy this over there. So the odds of okay. This let's copy this. Actually, do this. It's F is O11. This is O11 divided by O12. So give us the odds 0.26. We copy this formula into this space, so we get the odds uh, for high income family. So that's odds. So the odds for low income boys who belong to a Boy Scout is 0.256. The odds for high income boys who belong to Boy Scout is 3.344. Okay. Now let's calculate the odds ratio. Odds ratio. Odds ratio is simply the ratio between these two odds. Okay. Let's to make it easier, let's look at this. Let's highlight the low income family in one color, and highlight high income boys use a different color. Okay. So either these odds for low income boys are 0.256. The odds for high income boys is 3.344. Now let's find out the ratio between 2.56 and 3.44. That is so-called odds ratio. The ratio between the two odds is called odds ratio, and that is simply a O13. O13 divided by P13. P13. So that gives us odds ratio. The odds ratio 0.0765. Okay, now let's do one more thing. So we're going to calculate log odds ratio. Log odds ratio is simply we take natural log of this odds ratio. How do we do that? Let's go to this calculation with more. This is the natural log, ln natural log. So we select that. Okay. So what number you want to convert that into a natural log? We want to convert this value into a natural log. Okay. That gave a log value negative 2.57. So give us a log odds value negative 2.57. You may begin to wonder what is this number. Let's keep this for now. Let's copy the whole. Let's copy the whole table from here to here into the next spreadsheet. Next spreadsheet is the parameter estimate table. Let's copy this table to here. Okay. So we have this low income, high income versus the Boy Scout membership. Now let's change this to not expected count. Let's change that to parameters. Okay. We get rid of these four values because we're going to fill in this table with some parameter that we read from parameter estimate table. So these are all the parameter estimate table here. Okay. Now let's see what we have here. So we need to fill in these four space here. Okay. Fill in these spaces by using the parameters. So we have four parameter to fill. Parameter between Boy Scout, yes, and low income. So let's to make it convenient. We know that in Boy Scout variables, we have two levels. Level 1 is yes, so we call it yes as 1. Level 2 is no, so it's yes 1, no 2. But for income, you have three levels. Income low is 1, income high is 3. So now, based on this, let's look for the parameters values from the parameter table. Let's look at this table here. Boy Scout 1 and income 1. Okay. Boy Scout 1, income 1, the value is this. Copy this over to this table. Negative negative 1.363. Okay. Then Boy Scout 1, income 3. Okay. Boy Scout 1, income 3 is this value. Boy Scout 1, income 3, 1.207. Copy into this cell. Then this cell, Boy Scout 2, income 1. Boy Scout 2, income 1, 0. Okay, 0. And also Boy Scout 2, income 3. Let's see. Boy Scout 2, income 3, 0 again. Okay. Now, let's do one more thing before you can figure out, you can understand what we're actually doing. Let's do one more thing. Let's do we use this value plus this value minus this value minus this value. Okay. So we're going to calculate this value. Okay. So we use this value plus this value minus this value minus this value. Okay. So let's simply call it K7 plus L8 minus K8 minus L7. Let's see what we have here. Okay. See what we have here. Do you see that? We use this value plus this value minus this value minus this value. What we got here is negative 2.57. These values, we've seen it somewhere before. Did you realize that? Negative 2.57, we come to the table that we built before. Negative 2.57, what is that? That value is actually the log of ratio. Now we realize that the parameter estimates from log linear model actually can be used to calculate log odds ratio. The combination of the parameter estimates from a log linear model end up being the log odds ratio of a contingency table. Now the issue is that what does the log ratio tell us? So we need to look at where the log odds ratio come from. It comes from odds ratio. And what is the odds ratio? Odds ratio, as we know, is simply the ratio between two odds. One is the odds of boys who are member of a Boy Scout from low-income family. Another is the odds of boys who are Boy Scout member who come from high-income family. So this odds ratio simply tell us that the odds of boys who are Boy Scout member who come from low-income family is 0.077 times the odds who are Boy Scout who are from high-income family. Let me repeat. The odds ratio simply tell us the odds of boys who are Boy Scout membership who are from low-income family is 0.077 times the odds for boys who are from high-income family. Now, how much lower? You can really calculate how much lower is 1 minus 0.0. You can really do this calculation. You can really calculate equals 1 minus 0.14. Or is 92.3% lower. So the odds of boys who are membership, who are Boy Scout, who are low-income family is 92% lower than boys who are from high-income family. So that is what uh, this that was the what log odds ratio means, but also that is what we can get from the parameters of a log linear model. The log linear model simply allow us to obtain the information of log odds ratio. From log odds ratio, we can really get a sense of what is odds, and odds really gave us a sense of the meaning of this log linear model. From this log linear model, we realized that boys who are from low income family, they have odds of a to be a Boy Scout member 92% lower than boys who are from high income family. So that's exactly how we interpret the result of a log linear model. Now let's also look at now let's do another example. For this example, let's look at the relationship between delinquent and income. Let's calculate this table. Let's calculate this table. Uh, calculate the table to create a new table that shows the relationship between delinquent and income. So let's delinquent income family. So now it's not the boys, but not the Boy Scout, but delinquent. Let's calculate delinquent. Calculate delinquent word here. Delinquent, yes, means they are delinquent. No means they are not delinquent. Now, again, so we have to fill up this contingency table by looking at information from this count table. Now let's get rid of these colors so that we can be to have these values. Now it's a Boy Scout. No, it's a delinquent versus income. Now let's first look at those delinquent boys who are from low-income family. Now delinquent boys who are from low-income family. Delinquent, so this is a yes delinquent. Yes, delinquent. We have boys who are delinquent, but they are Boy Scout member. But also we have boys who are delinquent, but they are not Boy Scout member. So we need to add up this value with this value. So first value are the boys who are delinquent, but at the same time they are Boy Scout member. Second value are the boys who are delinquent, but they are not Boy Scout member. So that's is what we need to add up this value here. So that's get rid of this old information and try to, so that value, so this value is F4 plus F10. Okay, then for median income boys, this is this value. And the green, so that the boys who are from median income family who are delinquent. Okay. So that's F5 plus F11. Okay. And then we do boys who are from high income family. Let's color this. So with the color scheme, it's easy to track. Okay. And that one. Okay. So that is the boys. Okay. F6 plus F12. So these are boys who are delinquent. They're from low, median, high income family. Now, in the same way, we have to figure out the boys who are not delinquent, who are from low, median, high income. And these are this cell. Okay, this cell are the boys who are not delinquent from low income family, but who are Boy Scout member. And this value are the boys who are from low income family who are not delinquent, who are not Boy Scout member. So that is F7, F7 plus F13. And then for boys who are from median income family who are not delinquent, who are Boy Scout member, and the boys who are from income family, median income family who are not delinquent and who are not Boy Scout members. And this tell us is F from F8 plus F. Oh, sorry, from F. No, and F who are not delinquent. Not delinquent. Not delinquent. Nope. At the bottom part. The bottom part. Yeah. Who are from. Okay, from not A. It should come from not delinquent. Not delinquent. It should be. Oh yeah. It's 8 and 14. At 14. At 14. Okay. And finally, boys from high income family who are not delinquent, who are Boy Scout members, as well as the boys who are from high income family who are not delinquent but who are not Boy Scout. This tell us this is the part that tell us the blue part, the blue. Let me take the blue. Take the blue. Okay, so that is F9 plus F15. F15. So now we have this new continuity table. New continuity table that show the relationship between the delinquent and the income level. Okay, let's reduce the number of decimals. Okay, not here, right? Now let's focus on again a subtable. Let's focus on a subtable between median income and high income. Median income and high income. So let's copy this table to here and focus on part of this table. Focus on this. Okay, we look at the relationship between the boys' delinquency and income, the income with two levels. Okay, look at this. Okay. Again, for this, we like to calculate. Odds and odds ratio. Let's calculate these few numbers here. Copy this over. So odds of delinquent odds of boys who come delinquent from median income family is this, is 0.14. Okay, and odds of boys who become delinquent from high income family is 0.039. And odds ratio basically is this value divided by this value. That gives us 3.674, and the log odds ratio is 1.30. Okay, so remember log odds ratio is 1.30. Now let's go to the parameter table. Now let's look at let's first copy this copy this table to the parameter table so that we can look at the relationship. Let's type this into parameters, and we look at the relationship between delinquency and income. Again, we try to code this, so delinquent, yes, is level 1, and no is level 2. For income, median is level 2, high income is level 3. So now we're gonna look at these parameters that correspond to these combinations of levels of two variables. Delinquent 1, income 2. Delinquent 1, income 2. Delinquent 1, income 2 is this value, negative 1.121. Okay. Negative 1.121. Delinquent 1, income 3. Delinquent 1, income 3 is negative 3.239. Okay. Negative 3.3239. And delinquent 2, income 2. Delinquent 2, income 2, 0.817. And delinquent 2, income 3. Delinquent 2, income 3, 0. Okay, 0. Okay, so now we have the three values. Let's recolor them to make sure. Now we're going to do the same thing. This value plus this value minus this. We do the same thing as we did before. Copy this formula to here. Let's see what we got. We got 1.30, and that value looks familiar. What we got at before, 1.30. And again, try to figure out 1.30 is simply the log of the ratio. To figure out what is the log of ratio, we go back to odds ratio. The odds ratio is 3.67. So that odds ratio is simply the ratio between two odds. That tells us the odds of boys who become delinquent, who are from median income family, is 3.67 times the odds of boys who become delinquent when they are from high income family. See, the boys who are from median income family, the odds for them to become delinquent is 3.67 times the odds of boys who become delinquent but who are from high income family. How much higher? This is how much higher. It is simply this value, 3.674. Is 3.674 minus 1 is 2.67 times higher. In other words, 267.4% higher. So the boys who become delinquent, the median income family who become delinquent is 267.4% higher than boys who are from high income family. Now you can see that the parameters that we get from a log linear model actually mean something. The combinations of parameters from log linear model can be used to calculate log odds ratio, and from that you can get odds ratio. And from odds ratio you can interpret the meaning. Of a log linear model, and that exactly the function of a log linear model and the purpose of the parameters that you can get from a log linear model. I hope this helped. I see you next time. So next time we come back, we try to work on a log linear model that has more than 3 variables. How we interpret the parameters of a log linear model that have more than 3 variables. I hope this helped, and thank you very much. I see you next time. Bye now.